Okay. Yeah, thank you everybody for coming. I think you all know this is going to be a master's defense for Lindsay Mckenna. I'm here just as a formality to introduce Tom Lippman, who will introduce Lindsay for you.
Thanks, Chris. Thanks also for coming. We're going to have several introductions now. Okay. So I'm Tom Lippman. I'm Lindsay's thesis supervisor. This is her defense and ocean mapping course. And just want to say a few words about Lindsay. The first is she got her BS degree in geological sciences from the University of Brown University. Sorry, not University of Brown. That's a different place. That's an Ivy League school, I think, in 2007. And since then, she worked in industry for a few years for Malcolm Perney, doing environmental consulting in New Jersey, and then came to UNH in the fall of 2010. So she's been here now for, 3 years, 2.5 years. Okay, in that time, she's done a significant amount of field work. She's participated in a number of different nearshore field experiments, including in Hampton Inlet in the fall of 2011. She'll be talking more about that today. Also at New River Inlet in North Carolina in 2012 in the spring, and has participated in several cruises, including on the Healy and the Nautilus in 2012. And participated in a number of outreach activities for us. When she's all finished, she'll be pursuing several different options, including doing some Sandy research affiliated with CCOM, or even a Sea Grant Fellowship, which she's a finalist for, and she'll be pursuing that possibly in the next short time. Okay, before I turn it over to Lindsay, I want to introduce the thesis committee. In addition to myself, there's Larry Ward from the Department of Earth Sciences and CCOM, Yuri Razanov from Ocean Engineering and CCOM, and Diane Foster from Mechanical Engineering and the Ocean Engineering Graduate Program. Okay, so the format of the presentation will be Lindsay giving about a 45 or so minute presentation, and then we'll open up questions to the audience for a few minutes, and then we'll excuse the audience, and then the committee will examine the thesis with Lindsay for a short while. Okay, please welcome Lindsay. She'll be presenting her thesis on observations in bedform migration and current flows in Hampton Seabrook Harbor. Inlet.
Good afternoon, and thank you for coming. My thesis is titled Observations of Bedform Migration and Current Flows in Hampton Seabrook Inlet Harbor. And below we have a picture of the Hampton Seabrook Inlet area, and on the right is a picture of our survey operations from the field experiment. Before I get started, I want to thank NOAA and ONR for generously funding this research. I'll be starting today's presentation off with a brief description of the Hampton Seabrook Inlet, and then I'll briefly discuss why we want to study inlets and why they're important. And that'll lead me into my research objectives. Now I'll give you a brief outline of the steps we took to complete this study. Then I'll take a few slides to talk about historical dredging in this inlet. Dredging is an important natural resource issue in New Hampshire, so it's worth talking about dredging in the context of this inlet. Then I'll go into more detail of my methods, and then talk about my observations and results of first the bedforms and then the currents. And then at the end, I'll tie all those observations together and look at some of the spatial patterns we see in the inlet. So the Hampton Seabrook Inlet is located between the townships of Hampton and Seabrook in New Hampshire. It's located about 20 miles from here in Durham, where we are up here, and there's a study site. The inlet separates Hampton Beach to the north from Seabrook Beach to the south, and connects the Hampton Harbor estuary to the Gulf of Maine. The inlet opening is stabilized with jetties to the north and to the south here. And straight down the center of the inlet is a deeper navigation channel that's dredged and maintained by the Army Corps. The controlling depth of the navigation channel is about 8 feet or 2.4 meters. And the depths outside of the navigation channel are very shallow, sometimes under a meter during low tides. So inlets like this can be found all over the world's coastline, and they're important because they act as a highway between the ocean and the Back Bay areas. So this is another picture of the Hampton area. We have the Hampton Harbor estuary here on the left, the Gulf of Maine on the right. This is the location of the inlet. And a lot of marine animals, such as the alewife or smelt fish, they utilize the inlets to transit from the open ocean, where they spend most of their time, to the Back Bay areas to spawn and reproduce. Humans also use inlets regularly because most marinas are located in the back bay protected areas. And then mariners will transit through the inlet to access fishing grounds and then come back at night to dock their boats. Inlets are also important because they provide estuary flushing, and they're the main pathway between the saltwater, the open ocean, and the back bay areas. So that tidal flushing is really important for species such as clams or oysters, and it's also important for salt marshes. Hampton Harbor is home to over 4,000 acres of salt marsh, and it also has the most productive soft-shell clam bed in the state of New Hampshire. The fishing industry located out of the Hampton Harbor estuary area is estimated to be about $5 million in revenue per year. So hopefully I've convinced you that inlets are important, and now I want to talk about why we want to collect regular scientific data from them. And the first reason is for navigation. As I said, lots of mariners transit through the inlets daily, and they rely on paper charts to safely transit in and out of the inlet. So a lot of inlets are not only really shallow, but they also are sometimes characterized by large bedforms. And sometimes those bedforms can migrate and shift over time. So the next reason is dredging. A lot of inlets, like the Hampton Seabrook Inlet, are confined by jetty structures. So these jetties are really great at making sure the inlet opening doesn't shift over time, but they're also really great at trapping sediment. So when that happens and the depths get too shallow, the inlets need to be dredged. And as most of you know, to have a successful dredge, you need to know about the bathymetry and other oceanographic conditions. Another reason is for infrastructure. This is the Route 1A bridge that crosses the Hampton Seabrook Inlet. And so for engineers to design and build stable structures, they need to not only know about the bathymetry and oceanographic conditions, but about the sediment type and other. So the last reason is for modeling. Engineers, scientists, harbor masters, and the military are all interested in how inlet environments are going to react to different environmental forcings over time. And as most of you know, the more data you can put into a model, the more accurate those algorithms are. So that leads me into my research objectives. And our first objective was to map the seafloor in the navigation channel and measure the bedforms that are in the inlet. And once we were able to measure the bedforms, we were able to calculate migration rates. And our second objective was to look at the current structure. So how are the tidal flows actually moving the currents through the inlet? And then from the vertical structure of those currents, we were able to look at boundary layers and calculate sediment transport parameters. And then we compared those sediment transport parameters to the observations of the bedform migrations. And our last objective is something we haven't actually completed yet, but hope to down the line, and that is to take all of our observations and put them into a coastal or inlet dynamic model. So now I'm just going to briefly outline the steps of the study. And the first is we collected 9 bathymetric surveys of the inlet navigation channel over a month-long period. And from those surveys, we could map and measure bedforms. And from that mapping, we could measure migration rates of the bedforms. And we took those migration rates and compared them to the tidal cycle. We actually saw that the bedforms migrated with the tidal cycle. And the next, again, we took the current profiles and measured the sediment transport parameters. And we found that just like humans can sculpt sand into pretty structures, the tides through the Hampton Inlet are strong enough to form bedforms and actually move the sediment around. So now I'm going to talk about the historical dredging at the Hampton Seabrook Inlet. As I said, it's an important economic and natural resource issue in the state. Most all of the inlets in New Hampshire are dredged regularly. And not only do people feel that dredging can have negative economic or ecological impacts, it's also very expensive to complete dredging, on the order of a few $1 million sometimes. So between 1965 and 1987, the Hampton Seabrook Inlet Navigation Channel was dredged 13 times. And during each one of those dredges, roughly 20,000 cubic yards were removed during each dredge. And just for reference, a truck roughly this size can carry about 16 cubic yards. So that's over 1,000 of those bedload trucks worth of sediment moved either onto the adjacent beaches or somewhere offshore. But despite the regular dredging, the bedforms redevelop year after year. So these are aerials from 1978, 1986, and 1998. And you can see the presence of these bedform structures in all of these aerials. And between 1978 and 1986, the Inlet navigation channel was dredged 3 times. So to look at this in a little bit more detail, we digitized each of those bedforms from those 3 surveys shown before, and also included a survey from 2000, an aerial survey, and the multi-beam bathymetry from October 17th, 2011. And you can see that the bedforms are always in the navigation channel, and roughly in the same locations. And also the bedforms extend to the north of the Inlet navigation channel, still in the inlet in the more shallow areas. So this is an interesting question, an issue in the Hampton area, because there's no major river depositing sediment into the Hampton Harbor estuary. So unfortunately, I don't answer why these bedforms come back and redevelop year after year after dredging, but what I do look at is, once they're in place, how do they move and migrate over a month-long period? So are they continuously migrating offshore? Are they continuously migrating onshore? Over a month-long period, do they remain stationary? Or is it some sort of combination of all of that? So to look at that, we focused just on the navigation inlet channel area. We did survey offshore, but I won't be discussing those results for the rest of the presentation. So I'll go into my methods in a little bit more detail. All of our surveying took place in the fall of 2011. We surveyed over 7 days between September 21st and October 17th. We collected 9 separate bathymetric surveys. On October 5th, we actually collected 3 separate individual surveys over a 12-hour period. So all of our bathymetry surveying had to happen during high tide. We weren't able to actually be in the inlet channel during low tide because it was too dangerous and because it was too shallow. So all of that surveying was on the high tide. And October 5th, we surveyed twice during the first high tide of the day, and then once again for the second high tide of the day. We also surveyed the currents on these same days, but we weren't confined to surveying currents during just the high tide. We could also survey during low tide. So we collected current measurements using acoustic Doppler current profilers. We had 3 bottom-mounted ADCPs. We had 2 located offshore in 7.5 and 12.5 meters of water, and these were attached to tripods like this. And they had 1 ADCP actually in the inlet channel, but off to the side of the navigation channel. And then we also, and the bottom-mounted ADCPs recorded currents continuously over the entire duration of the study. And we also collected currents using the Coastal Bathymetry Survey System, or also known as the CBAS, which is a personal watercraft equipped with a GPS, an ADCP, and a single beam echo sounder. So we collected currents along transect lines oriented along channel and across channel. We also collected the currents over the 2 offshore ADCPs, and just for reference, this is the location of our onshore and inlet ADCP. So for each one of these transect lines, we actually transited and surveyed 10 times. And then all of that data over either a 15 to 60 minute period went into calculating mean currents over that period. So the spatial averaging was horizontally 30 by 30 meter box and depth bins of 25 centimeters. And the reason we had to calculate mean currents is if you think about a vessel like this going over waves or boat wake or during a strong wind, anytime that vessel moves, the current reading is going to be affected. So if you think of a surface wave as a sine wave, sometimes you're going to go over the wave during the crest and sometimes during the trough. And then if you go over that area 10 times, you'll hopefully average out those surface velocity variations. Moving on to the bathymetry. All of the bathymetry was surveyed aboard the RV Coastal Surveyor, which is equipped with an Aplanix POS MV 320 inertial motion unit. And to the front ram of the boat, we attached an Imagenix Delta T 260 kilohertz multi-beam echo sounder. We collected sound speed profiles at roughly hourly intervals from the mouth of the inlet channel using a Digibar Pro. And I also wanted to mention that both the Coastal Surveyor and the Sea Bass received RTK GPS corrections from a base station we had set up on this house in Hampton Beach. So bathymetry survey lines were oriented in the along channel direction, and they were spaced at 10 meters. And for each survey, at least 2 full passes of the inlet channel were conducted, and all that data went into one survey. So we would survey lines 1 through 10, and then go back and repeat survey lines 1 through 10. And then from all that data, we would create one bathymetric surface. Initially, all our depths were referenced to the ellipsoid, and they were later re-referenced. So this is our data product. This shows the bathymetry from October 17th. It's gridded to 25 centimeter resolution using the cube uncertainty algorithm in Keras. And you can see these large amplitude bedforms oriented across channel. We classified these as sand dunes. And they have amplitudes in the order of 1 to 2 meters and wavelengths of 20 to 40 meters. And superimposed on top of these sand dunes, and also located in flatter portions of the inlet, are smaller amplitude megaripples. And the megaripples had amplitudes on the order of 10 to 30 centimeters and wavelengths of 1 to 10 meters. I also want to point out these large scour ripples located just seaward of the bridge pilings. They're really interesting features, but we won't be focusing on them for this talk. The rest of the talk will focus on the observations from roughly 200 meters away from the bridge to about 800 meters away from the bridge, which is the main portion of the Bedform field. And what good is a bathymetry surface without uncertainty? So I calculated a few different uncertainty measurements. The first was to calculate the attitude and positioning uncertainty, and I did that using RMS errors that were output from Aplanix POSPAC software. I was also able to estimate a horizontal and vertical component of the sound speed from Johnny B's SVP editor program. Now, unfortunately, Keras doesn't have a built-in acoustic uncertainty model for the Imagenix Delta T, so I was unable to get accurate total propagated uncertainty from Keras. So I created my own acoustic uncertainty model. I used data from October 17th, and over 300 pings, and I used a paired estimation method where I looked at the range differences between successive pings as the standard deviation of those range differences as a function of beam angle. So at nadir here, the acoustic uncertainty is roughly about 2 centimeters, but about 40 degrees away from nadir, that standard deviation error jumps up to about 4 centimeters. So because I was unable to get really good estimates of total propagated uncertainty, we looked at uncertainty with a different method known as the noise floor. And we did that by calculating spectrum and looking at the noise floor of the spectrum. And this tells us roughly the resolving capability of the overall survey, incorporating all forms of uncertainty and error. So I'll go into a little bit more detail of how we calculated the spectrum later, but in general, we broke up each survey into smaller boxes, calculated on ensemble average sample spectral density. And then if you think about a spectrum, the portion of that spectrum where it flattens out, the higher wave numbers or higher frequencies, gives you your noise floor. So I contoured up all the noise floor values for each of those more individual boxes, and they're plotted up here. The color bar shows the noise floor in meters. So we go from 0 in blue up to 5 centimeters in the dark red. And for almost all these surveys, the noise floor is less than 2 centimeters. On September 28th and September 30th, the uncertainty goes up to about 4 or 5 centimeters. And that's because we had really strong currents and also higher amplitude waves in the inlet for those days. So hopefully I've convinced you that we can resolve features on the seafloor and the vertical on the order of a few centimeters. And so we wanted to look at the bedforms in a little bit more detail. So to do that, we took each of the Keras surfaces and reprojected and rotated them into a local coordinate system. So the new origin is located here at the center of the bridge, and our new x-axis represents a long channel distance in meters from the origin, and the y-axis represents a cross-channel distance from the origin in meters. We re-reference the depths to NAV-D88, which is close to mean sea level here in New Hampshire. So the new color bar shows negative 2.5 meters in red to negative 7.5 meters in blue. We did this for each of the survey days, and you can clearly see the presence of the sand dunes in every single surface. However, it's really hard to quantify what the bedforms are doing from day to day just by looking at surfaces like this. So our first method for actually measuring bedform migration was to take a difference plot. By taking a difference plot, we would subtract one surface from the next. And we first did this over the entire study period. So we went from September 21st to October 17th. And the colors now represent change in elevation in meters. So the red represents 1 meter, positive change, and blue is negative 1 meter change. You can also think of that as blue representing places where there's erosion and red representing places where there has been deposition. So over this entire study period, you can clearly see that these sand dunes migrated offshore roughly 10 to 20 meters. So then we wanted to look at the differences between successive surveys. So we created difference plots between each successive survey date. And we actually could measure the migration rate in meters per day. And we represented the rate with arrows. And they're scaled up here. This is 6 meters per day. And the red represents an offshore migration, and the blue represents an onshore migration. So we took each of those arrows and superimposed them on a tidal chart below. And you can see that during spring tide, we have a net offshore migration. The tidal range during spring tide is almost 4 meters. But during neap tides, we see a net onshore migration. And the tidal range is much smaller, about 2 meters during neap tide. So the difference plots give us a really good idea of the net integrated volume change in sediment in the inlet, but it doesn't do a really good job at showing us the orientation or the shape of the individual sand dunes. So to do that, we did a little bit more traditional method of bedform mapping called crest mapping. So we used a Bishnu algorithm, which was initially developed for fingerprint analysis, and Yuri's actually modified that algorithm to determine topographic highs and lows from grayscale bathymetric surfaces. So when we ran the Bishnu algorithm, it objectively picked 8 crests and their corresponding troughs. And those crests were labeled crests 1 through crest 8. And the crests on September 21st are shown in blue, and on October 17th, they're shown in red. And again, you can clearly see that the net migration over the entire study period is offshore. It's really hard to determine what's happening between successive surveys with this method, because if the bedforms haven't actually moved that much, it's hard to see those changes just by looking at crests. However, what you can see is that a crest doesn't migrate at the same rate over even just the length of one crest. So for example, crest 6 here, you see the northern portion of a crest has only migrated about 6 to 8 meters offshore. However, the southern portion has migrated almost 20 meters over the same time period. So to look at this with a little bit more detail and to look at the actual shapes of the crests or the bedforms, we took long channel profiles across 50 meters here and 25 meters here. And this is the resulting plot. So these each represent the long channel profile for each survey day, and each profile is offset by 1 meter from the next, so you can see the changes. The top is the 50-meter profiles, and the bottom is the 25-meter profiles. So we calculated a left and a right slope of each sand dune, and we couldn't really actually determine any patterns in what the shapes of the crests were doing in regards to the tidal cycle. However, we did see in general that the amplitudes of the crests were greater in the northern portion of the inlet than in the southern, and that some crests have symmetrical form. Crest 5 and crest 6 here seem to be pretty symmetrical. However, other crests or other sand dunes have more asymmetric forms. So crest 2 has a steeper right slope, and crest 3 has a steeper left slope. And the other thing you can actually see from these profiles are these megaripples. But it's really hard to determine which megaripple is which from one survey to the next. They don't quite have the same signature that the large sand dunes have. So to actually look at the megaripples in a little bit more detail, we actually looked at the roughness elements of the megaripples. And we did that by using spectral analysis. And the first step for that was to filter out any large wavelengths from the surface. So this plot up here represents any wavelengths that are less than 12 meters. And then we broke up the surface into these smaller boxes. They were 50 meters by 18 meters. And we placed one of those boxes across the entire transect. And each box had a 50% overlap from the next. And then in each individual box, there were 72 long channel separate profiles spaced at our grid resolution of 25 centimeters. So we calculated a spectra across each one of these individual profiles and then did an ensemble average of all of those spectrum to get a sample spectral density of the entire boxed area. So that's represented here on the right. And then we broke up that spectrum into wave number bands. And the first wave number band we looked at was the 5 to 10 meter wavelength band, and then the 1 to 5 meter bands. And then we wanted to calculate the RMS amplitudes of those bands. So to do that, we looked at the area underneath the spectral curve, which gave us variance, and then we were able to calculate the RMS amplitude from this equation. And that's based on the Rayleigh distribution. And before moving on, I just wanted to point out when I talked about the noise floor before, this portion circled here in the red represents the noise floor of this box. So then once we got an RMS amplitude of each individual box, we contoured up those amplitudes for first the 1 to 5 meter wavelengths. So that's what these plots represent. We go from September 21st to October 17th over here. And the color bar represents the RMS amplitude in meters, going from 0 to 0.4 or 40 centimeters. You can clearly see that things are changing, but it's a little hard to tell with the 1 to 5 meter wavelengths. It's a little bit more clear with the 5 to 10 meter wavelengths. And you can see that the amplitudes generally increase with the rising tidal amplitude. So from September 21st to September 28th, we went from a neap to a spring tide. And then the amplitudes decay as the tidal amplitude also decreases, going from September 30th to October 17th. So we next looked at the seafloor roughness elements over one day. So we did that for the October 5th data. We have the 5 to 10 meter wavelengths here on the left and the 1 to 5 on the right. And also shown is the tidal cycle just for reference. So the top is during the first rising high tide, the second one is during the peak of that high tide, and then the third one is from the second high tide of the day. And you can again see that the megaripples are changing in both space and time, but it's really hard to quantify individual and measure actual separate amplitude changes just by looking over one tidal cycle. So now that I've talked about bedforms and described both the sand dunes and the megaripples, now I want to move on to the currents and talk about the current observations that we saw. So before I do that, I need to convince you that the currents we measured from the sea bass system are accurate. So we did that by comparing the currents measured from the sea bass ADCP to those measured from the bottom-mounted ADCP. And this represents line 8 across one of the bottom-mounted offshore ADCPs. It's a cross-section along the line, and it shows current magnitude. The dashed vertical line shows the location of the bottom-mounted ADCP. And from just this plot, you can see one of the advantages of using a moving survey system to measure currents. This large current plume was captured by the sea bass, but might not have been captured by the bottom-mounted ADCP. So the next step was to look at a comparison between the magnitude and the direction of these two systems. And that's what these plots on the right here show. The top shows the magnitude of the currents. The red dots represent what was measured by the ADCP that was bottom-mounted, and the blue represents those measured by the sea bass. Same for the bottom here, but for direction. So you can see there's really good correlation between the two systems. But maybe we just got lucky with that one measurement. So the plot here on the bottom shows all the measurements where we actually crossed over a bottom-mounted ADCP and compared to the sea bass. The left is direction, or magnitude, and the right is direction. And you can again see really good correlation. The R squared for both of these plots is over 0.95. So hopefully I've convinced you that the sea bass is accurately measuring currents. And what these plots represent are wherever we took currents straight down the center of the channel, so it's a kind of a long channel transect of the currents, and it's looking at a cross-section of them. And all of the measurements from the study period categorized by flood stage. So we categorized the floods by neap flood, neap ebb, spring flood, and spring ebb. And you can see that the currents are clearly stronger during spring tide, which is as expected because the tidal range is 2 meters greater during spring tide than during neap tide. Maximum currents during spring tide are 1.5 meters per second, and during neap tide, they're only 1 meter per second. The other obvious observation from these plots is that during flood tide, the currents actually accelerate around 800 meters along channel, and that actually lines up with the end of the northern jetty. So as the currents and waters moving onshore, they get trapped by the jetty and accelerate into the channel. So we wanted to look at the current structure with a little bit more detail, and we did that by looking at the vertical flow structure in individual transects. And so this represents September 28th currents along line 4. So we start here, lines up with the left side of the plot, all the way across. And you can see that in the southern portion of the inlet, the magnitudes are generally very low. Again, the colors on these represent, or reds are faster currents and blues are weaker currents. The fastest current plume is right over the inlet navigation channel, and the currents are not as strong off to the northern side of the inlet, but they're still stronger than they are to the south. So we looked at the vertical structure in the area delineated by these black dashed lines. And those average currents are plotted here in the blue dots. We did a 2-bin averaging, so this is binned in an average over 50 centimeters instead of a 20 centimeter average with depth. And you can see that in the upper portion of the water column, the currents are fairly uniform. But in the bottom portion of the water column, the magnitudes decrease with increasing depth. So we took this profile and plotted it on a semi-log Y chart, and you can see the presence of a linear log boundary layer. And when that log boundary layer exists, we can calculate sediment transport parameters. And so we calculated a few parameters, the first being friction velocity, or U star. And that's a potential measurement of how much sediment transport there will be. So if we're thinking about uniform grain size, because the friction velocity characterizes the hydrodynamic shear in the boundary layer, if we have a uniform grain size, then the higher our shear, the more amount of transport we would probably expect. So we calculated this value, the U star, using this equation, which is the current magnitude equals to U star over the von Karman constant times the natural log of Z, which is the depth of each current measurement, over the depth where the current would approach 0. And for this example from the previous slide, we see that our U star value equals 0.18 meters per second. So we can use that U star value to calculate a Shields parameter. And the Shields parameter, when compared to a critical value, tells us when we would expect sediment transport to be initiated. So if our Shields parameter is greater than our critical parameter, then you would expect sediment transport to be initiated. Although if it's smaller than that critical value, you wouldn't expect sediment transport to exist. So for this example, our Shields parameter equals 2.38, and it's roughly the drag force over the immersed weight of the sediment grain. And then we calculated a critical Shields parameter, and we could do this over the entire inlet, not for each example, because we assumed a median grain size of 0.85 millimeters everywhere in the inlet. Each sediment sample we took, that was our median grain size, so we just assumed that over the entire inlet. And we were able to calculate the critical Shields parameter based on empirical observations that have been calculated in the past, and we came up with critical Shields parameter of 0.05. So clearly, our Shields parameter is much greater than our critical Shields parameter, and you would expect sediment transport. So then we took anywhere where we took current measurements and could actually measure a boundary layer, we calculated both a U star and a Shields parameter. And then I categorized each of those measurements according to tide stage. So again, flood, neap, and spring, or neap, flood, and neap, ebb, and spring flood and spring ebb. And I averaged all those values in each tidal category together. So you can see here, this is the Shields parameter here and here. And during each tidal stage, our Shields parameter is always much greater than the critical. Even with these high sigma values, we would still expect sediment transport to be initiated, except maybe on a neap flood when we're not seeing a lot of sediment transport anyway. And the next parameter to look at is the U star friction velocity. And if we look at just the neap friction velocities, you see that the number is greater during flood than during ebb. And this is consistent with seeing an onshore migration during neap tides. Conversely, if you look at the spring values, you see that the ebb friction velocities are higher than the flood friction velocities, and we see a net offshore migration over this period. And then if you look at all the friction velocities together, you see our highest value is during a spring ebb tide, and we did see a net offshore migration of up to 10 to 20 meters offshore. So now I want to put all the observations together and look at some of the spatial patterns we see in the inlet. So this is a lot of information. I'll step you through each panel first. So the bottom here shows the bathymetry that was collected on September 28th. There's a profile line straight down the middle of the channel, and these correspond to the profiles we see in the top 3 plots. So this middle panel here shows the current magnitudes along that profile, and also you see the bathymetry measured from the multi-beam and as a cross-section. We categorized each of the crests, shown here and labeled them. And then the top panel shows wherever at 40-meter intervals we took our vertical current structure. And anywhere that we saw a boundary layer, a linear log boundary layer, that's shown in red, right here. And then from those we were able to calculate the U star values. And those U star values are shown with stars down here. And also on this third panel, you see the RMS amplitudes of the 1 to 5 and 5 to 10 meter amplitude megaripples. So the 1 to 5 in green and the 5 to 10 in blue. And I think the first noticeable spatial pattern you see is that during this flood tide situation, the currents are actually weaker over the crests than they are over the troughs. So if you think back to our highway metaphor, you can think of the crests being speed bumps to the current flows. Closer to the bridge, you see that the amplitudes of the megaripples tend to be slightly larger, but the amplitudes of the actual sand dunes are smaller. And you see in the top portion of the water column in this portion of the inlet tends to be more uniform than you would see further offshore. So this study could be greatly expanded upon if we had measurements of the inlet during low tide, and also if we collected measurements of current and bathymetry simultaneously. So for this study, we collected the bathymetry and the currents from 2 separate survey vessels. And although they were done close in time, they weren't exactly simultaneous to each other. But fortunately for us, Tom and John have successfully integrated the Delta T Imagenics multibeam onto the CBAS system. So look forward to some really interesting studies and surveys in the future. So in conclusion, we characterized the Hampton Seabrook Inlet channel by collecting repeated bathymetric surveys over a month-long period. We found that the channel was characterized by sand dunes and megaripples, sand dunes on the order of 1 to 2 meters in amplitude with wavelengths of 20 to 40, and smaller amplitude megaripples that had wavelengths of 1 to 10 meters. We were able to measure rates of sand dune migration by using a variety of crest mapping techniques. And we saw that during spring tides, the bedforms migrated offshore, and during neap tides, they migrated onshore. And over the entire duration of the study period, there was a net offshore migration. We looked at seafloor roughness elements using spectral analysis, and we saw that the amplitudes of the megaripples did change over space and time throughout the entire study period and over one daily tidal cycle. I also showed you that the correlation between a bottom-mounted ADCP and between an ADCP on a moving survey vessel was good, so we could accurately measure currents in the inlet from a moving survey system. And we measured currents and saw that currents were 1.5 meters per second during spring tides at a maximum, and only a maximum of 1 meter per second during a neap tide. And then we were able to calculate sediment transport parameters. And from the vertical structure of the current flows, we saw that we always were initiating sediment transport because our critical shields parameter was always much lower than our calculated shields parameter. And our U star values actually predicted what we actually saw with the bedform migration. So we saw higher U star values when corresponding to the offshore or onshore migration. So I'd like to acknowledge first my committee, Tom, Larry, Yuri, and Diane, for all of their help. And next, I'd like to thank Captain Ben and Captain Emily. Without you safely operating the Coastal Surveyor in often less than ideal situations, this study would not have been possible. And thanks to Jim, John, and Zach for providing all the rest of the fieldwork support. And Larry and Andy for giving me the opportunity to join CCOM. And lots of other faculty members who answered countless research questions and helped with hours of technical troubleshooting. This is just a few, you guys: Brian, Sema, Johnny B, Roland, Glenn, and Val. CCOM staff, especially IT, for helping me with my computer problems, especially this last week because my computer needs to be rebuilt. And Colleen for helping make really pretty pictures for all of my announcements. All my fellow graduate students, my parents, and my brother. And last but not least, everyone here at CCOM for making the last 3 years great. Thank you.
Okay, we have time for a few questions. And feel free to raise your hand. I'll just let Lindsay sort of.
Larry?
So I know you said you weren't going to talk about it. Where's the sediment coming from and where's it going?
Well, I can't answer that because.
Well, yes, come on.
Well, I'll tell you why I can't answer it. It's because we didn't measure the whole inlet. So we know that the bedforms exist outside of the navigation channel, but we could only survey in the navigation channel. So hopefully that's something Tom can explore in the future.
You're saying there's a net offshore
Yeah.
transport, so it's got to be coming from somewhere.
I think that, so we only looked at over a month-long period in the fall. I actually did, as part of my thesis, I looked at aerial surveys over a month-long period, over a month-long time scale. So they did some work in 2004 and 2005 where they had aerials once every month. And so I digitized those bedforms, or the sand dunes from those aerial images, and you could actually see that sometimes there was actually an onshore net migration from month to month. So we're only looking in the fall, but maybe in the spring or maybe during more periods of greater storms, there would actually be a net onshore migration. So that's one of the answers. The second is I think there might be some sediment bypassing coming from the Hampton Beach itself. But again, we can't actually measure those without having a full sediment budget, which we would need all the bathymetry.
Okay.
Sorry if that's unsatisfactory.
Well, it's very political. Politics.
Jim?
You're talking over your month-long period there, even though it's a small snapshot in time.
Mhm.
Do you have any estimate of what volume was transported? Because you have a waveform that you moved the measured amount.
In terms of how much sediment was moved?
Yeah.
I didn't do
So
any.
if the waveform moves a little bit, you got that volume of sediment that's moved.
Mm-hmm.
Do you have any estimate of how much sediment was moved in your 800-meter section there?
I didn't measure that. It's a good idea. I can do math in my head if you're thinking about a 2 meter. Are you talking about how much moved or how much actually was lost?
Moved.
Moved?
Because if the loss has got to be smaller, there wouldn't be a dredging problem.
If what was not smaller?
There wouldn't be a dredging problem if it was all lost.
Yeah. Well, we do know that it is coming back on shore. No, I don't have an estimate of how much. So let's see if we're looking at roughly 8 sediment dunes with 1 meter amplitudes on average. And they're 100 meters, 1,000.
That'd be interesting to see that.
Okay.
And
Yeah.
secondly, in answer to
8,000.
Larry's question, there's this infinite pile of sediment on land somewhere.
Yeah.
Help.
I mean,
Could you go back like 3 slides?
Yep.
I didn't quite understand.
This one?
Yeah. 'Cause
Okay.
Here you're saying the current velocities, now, is this the magnitude of the current?
Magnitude, yep.
This is the long?
Along, right across in the along channel direction. See where the black, I know it's hard to see, it's
This is
across the black
a
line.
long channel?
Yeah.
So you're saying that the velocity is lower over the peaks and stronger
Yeah.
over the
That's
troughs?
not what we would expect.
How do you satisfy continuity or transport? Because you've got less volume of lower velocity water on the crest and more depth, more volume at higher velocity.
Well, during September 28th, we saw that net migration offshore. So this is in the other direction. So maybe that's why we see a net offshore direction. So this is only on an incoming tide, this image.
He's asking though about
Oh.
continuity. You've got stronger flow in the trough than you do over the crest. So where does all that flow go?
Yeah, there has to be,
There has to be-
in order to have a stronger velocity in the trough, you have to get more water in somehow.
There has to be an across inlet transport.
Yeah.
Let's go sideways.
Yeah.
Yeah.
There has
So
to
there's
be-
probably a horizontal component if you're looking at the whole inlet system.
Because that would be interesting, because if the significant velocity is across channel, then there ought to be a lot of activity.
There-
Across channel.
Was this pattern true for all of your cases?
So we didn't have very many across channel or along channel profiles like this for the spring tides. So for the rest of the profiles, the currents were not really separated like this, and they weren't nearly as strong. But on 1 or 2 of the other days, we did see, not quite to this extent, but yeah.
Did you see the reflection in the current patterns of the bathymetry? That is the variability in the currents on average. Do you see it reflected in the current patterns? When you showed your spring and neap tidal cycles and you showed the average currents for those periods, did you see a relationship between the bottom sand dunes and the flow patterns themselves?
Well, this was the only one where we really could see
No, I
it.
meant the average over the neap and spring tides. There's
Okay.
variability in the current patterns.
Yeah.
In the along channel direction. Did you see a reflection of the average of all the currents in that?
Oh. I see what you're saying.
There.
Not really. I don't.
I actually think you see one.
You see that? So like down here?
Now, on the far right one, you can kind of see how the variability in the
Yeah,
structure
okay.
of the current follows
With this one here.
somewhat the sand dune patterns, and that's on average of all.
Yeah, but this, yeah, I guess you just have to look here, because this is the end of the inlet. This is going to 1,400 meters offshore. Lee?
Given that this is a dredged channel in this estuary, would you expect to see more or fewer waveforms if it was not dredged?
Well, I think it would fill in if it wasn't dredged. So probably not as high amplitudes for the bedforms.
That would be something like equilibrium then? Would that be
Yeah, it
more
would
of a
probably
steady
reach.
state?
So one of the interesting things about the history of the channel, if I can take it back that far, is they didn't build those jetties until the 60s. And before that, you saw a really big ebb tidal delta just offshore of the inlet channel. But then they built the jetties, and that's when you first start seeing the bedforms appearing. So I think that the actual jetty has a lot of influence on the current structure and trapping sediment and creating these bedforms.
So is there no ebb tide delta now?
Not nearly as big, no. And then offshore, so if the end of the jetty is right here, offshore in this area, there's some shoaling with some rocks. So that could be another place that sediment's getting trapped. If it is, the long channel direction is from the north to the south in the area, but maybe some of that sediment's getting trapped in those shoals and then being pushed onshore during a strong wave event. But I do think that the channel would probably fill in with more sediment, but I think you'd still see those bedform patterns at a certain depth. If it got too shallow, and you can see them. But just because the way that the jetty is actually structured and oriented, it's really crazy. Just anecdotally, look at the surface currents, and there's a lot going on. Okay, Ben, and then Yuri.
After this experience, now that we know that the jet ski can use the multi-beam on the jet ski, do you think you could get more complete data sets, less holidays in your data if you had done the multi-beam with a jet ski rather than with a larger boat?
Yeah, probably. I mean, one of the reasons we had a lot of the holidays is because it's an inlet and boats are navigating in and out. And if you're on a survey line and speedboat's coming in, you gotta move out of the way.
Yeah.
So I think with a smaller vessel, you could probably slow down a little bit, wait for them to pass, and continue. When we were down in New River, we didn't have nearly as many of those holidays.
Yeah.
So, and we're also doing, because you have to, with the currents, go over each line 10 times, we'd have to do the same thing with the bathymetry. So that'll help. Not only will we have 2 lines going into a surface, you're gonna have 10.
Yeah.
So it'll really help, but
Yeah.
it'll take longer.
Yeah.
Yuri.
I was wondering, right now they are dredging as much as they need for certain vessels to pass, right? So if they would need for larger vessels, would it be possible at all? Or this dredged channel would fill in immediately because of the transport of sediment?
I think they could probably dredge it deeper. The sides are pretty steep as it is, so I think it would probably have something to do with your angle of repose on the sides, with how deep you can actually make it.
Well, you can do it infinitely, right?
No, and then
Not
eventually you're gonna
infinite.
hit the bedrock too.
Yeah.
So I'm not exactly sure how deep the bedrock is in that area, but the actual Hampton Harbor is really shallow once you're in the harbor area, so I don't think you could actually get many deeper draft vessels in there to begin with. We had some issues going in and out. We actually
I
docked.
wouldn't want to go through that bridge with anything big.
Yeah, and just the currents through the bridge are crazy.
Really.
What's the target depth for the dredging? Like
It's 8 feet, which is it's like 2.44 meters.
below,
Mean lower low water.
That's so-called project depth by Army Corps.
Yeah.
so roughly where would that be, like if you were just to cut off those, how much are those bedforms, how much are they sticking up above that?
So this is nav D88, lower low water about 4 meters. Here? Probably?
No, mean lower low water's,
What?
mean lower low water's probably
You think?
maybe minus 2 meters or something like that? Because the tide range is 4 meters.
But it's the mean of your low water.
Meaner of the lowest low, and that's gonna be the spring tides.
Oh, yeah, 2.
So then you're
Force
gonna
the
drop
whole thing, yeah.
another, so
Yeah.
you're gonna be
Yeah.
dredging those sand dunes off, more or less.
Mhm. And I don't know if they dredge how if they even get down here and dredge. I don't know, how do they control what they're actually dredging in terms of
They
just
survey
sand and
like
stuff?
crazy.
Okay.
Yeah. Yeah.
I have two kind of small questions. The first one might be related to the continuity question about why current's slowing down over crests. Do you see any evidence of like standing waves on the surface of the water in terms of the along channel surface of the water changing in a static way as you go along the channel?
I mean, we see things changing in a horizontal direction
Mhm.
and in the vertical. So not only are the currents just coming straight in and straight out, but there's a lot of the cross channel. So
You don't see any like standing waveforms in
well,
the
closer
surface?
to the bridge, they
Okay.
were seeing some of that, but we weren't surveying.
There were some instances of supercritical flow.
Yeah, the
near the
hydraulic
bridge.
jumps.
Yeah.
Yeah,
And
but that was closer to the bridge,
Okay.
I think.
And I guess it kind of ties into, I'm curious about these changes in the surface of your current data here where you have dips and some jumps there. Is it
Mhm.
just that data near the surface were noisy or?
I think there's a feedback between the bed forms and what you're actually seeing in the current flows. So,
I think he's asking about the top of the water. As you move down the channel, it changes. And that's because some of the data was averaged from a different time,
Okay.
time.
Okay.
So it's sometimes we didn't have any data at that tide to be averaged into that point.
Okay. And the other question I have is, when you were looking at your acoustic uncertainty and you picked October 17th to run your own model, why did you pick October 17th?
I already had some of that data input into MATLAB, easily accessible.
Okay.
And October 17th is the day I didn't have a lot of holidays,
Mhm.
so I knew I was always getting estimates in depth from everywhere. Whereas some of the other times, it avoided the problem of having to look up timestamps and compare where in Inlet I actually was. So I just knew I had complete coverage on that day. That's the other reason.
Sort of relating to what Larry had asked, I was curious if, because you did see, I guess, about up to 20-meter migration seaward, did you see, using the crest finding algorithm, find anything new forming on the landward side of the channel? Any new sand dunes forming? Or
I had
just
actually cut
migrating
off,
into the studying area?
I cut off the image that I put into and applied the algorithm to at 800 meters, so I wouldn't have seen that, but the seafloor is generally flat and there's no mega ripples offshore of the jetty, so.
But if, they were migrating seaward, did you see
Yeah.
anything coming from the bay area into the study area?
No. Tom?
Could you speculate a little bit on future applications of what you've learned here, like maybe building transport models or flow models, or maybe redesigning like the jetty?
How I would do it?
No,
I'm not an
just can you
engineer.
speculate at all at future
Yeah,
applications?
I think one is to first apply these observations to a model, but the reason we can't do that now is because, again, we only have observations right down the center. I mean, the whole inlet is a system, so you've got these really shallow areas outside the navigation channel having a significant impact of what's happening in the navigation channel. So if we applied just these observations to a model, it would kind of be an incomplete picture. But what I think it can tell you is maybe if there's a model where you can say, well, this is how it acts with the jetty. How would it react if you took that jetty away and the flows were able to just come in and not get deflected around that jetty? When we're actually surveying in the inlet, if you just look off the side of the boat, the currents that sweep in around that jetty that sticks up to the north are really, really strong. And we don't have measurements from there, so it's too dangerous to get that close to a big stone jetty with either a jet ski or a boat. But I do think that interaction, the jetty has a lot to do with things. So I think it'd be really interesting to model if you took the jetty away. But then the problem of the jetty is you're gonna have more erosion on Hampton Beach, and Hampton Beach is a really big economic resource in New Hampshire. So it would be bad if there was no beach for people to go to anymore.
Okay, I think we'll, do you have one more question?
Yeah,
Okay,
I
one
finally
more.
managed to figure out what I wrote here. And that is, the ADCPs do measure backscattered amplitude, which you can use to get some estimate of the amount of suspended stuff in the water column. Did you look at this data?
No.
That might-
Did you, Tom, look at the backscatter?
We have not. I mean, the
Okay.
grain size is, what, 0.85 millimeters on average? So you would potentially see something, but the finer sediment is the stuff that's up in the water column high. The heavier stuff is down near the bottom, the bigger stuff. So it's, I don't think we're gonna see a whole lot from the moving platform about anything sort of in a comprehensive way. We know there's a lot of sand moving, but
Because, I mean, Sander has a little bigger size, and even if you're in the Rayleigh scattering regime, you might be able to get something.
we might try that.
I just didn't know if you looked at it or not.
I haven't discounted it before we even got to that point. Okay, well, we'll call it there, and thank you very much.